All right, let's take a look at our fourth example from Chapter 6. A well-insulated steam turbine generates power by expanding steam from 30 to bar from 30 bar 450 degrees C to 8 bar. Determine the amount of work and the exit temperature if operation is reversible, and then we're asked to repeat the calculation assuming an efficiency of 80%, and then how much is the lost work due to the reduced efficiency. All right, let's give it a try. So first I'm going to start with a picture. Okay, so here's my picture of my flow device, which in this case is a turbine. I have steam at a temperature of 450 degrees C and a pressure of 30 bars. So my inlet stream is fully specified. And coming out of my turbine, I have steam. I don't know the temperature, but I know that P2 is equal to 8 bar. Okay, so my exiting stream is not fully specified, at least not yet. We're told that our system is well insulated, so I would take that to mean is that Q is equal to 0. There's no heat exchange between my system and surroundings. And that's it. And we're also told that operation is reversible in A. All right, so in A, we're told that we have reversible operation. Okay, so we're told that we have reversible operation. Q is equal to 0, right? We're going to assume this is adiabatic since my turbine's well insulated. And we want to determine W, right? The amount of work produced along with the exiting temperature, T2. All right, how are we going to do that? Well, let's take it one step at a time. And are we told anything about a bath or anything of that nature? No, and I guess it doesn't matter. We're insulated. All right, so I'm going to start with reversible operation and see if that gets me anywhere. Okay, reversible operation tells me that my entropy generation is equal to 0, right? Or equivalently, in terms of an open system, my rate of entropy generation is equal to 0. Okay, well, when I write down my entropy balance, I like to think in terms of Chapter 4, and the S-gen is equal to delta S of my system plus delta S of my surroundings, where, I'm going to assume that my surroundings can be treated as a bath. Okay, well, for bath, delta S of my bath is equal to Q bath over T bath, where Q bath is equal to the negative Q of my system. Okay, and since operation is adiabatic, right, Q is going to be equal to 0. Okay, so delta S of my bath is just equal to 0. Okay, so I'm left with then S-gen is equal to delta S of my system, which is equal to 0. Okay, cool. If I want to write this in terms of a rate, I would have that S dot gen is equal to M dot S2 minus S1. Okay, I'm assuming my mass flow rate is constant, or if I want to divide through by mass, right, I would just get S-gen as S2 minus S1. Okay, in this case, it doesn't even matter since S-gen is equal to 0. Okay, so what I'm left with then is it must be that S2 is equal to negative S1. All right, so this is great because then my system's fully specified. Since I know T1 and P1 of my inlet stream, I could go to my steam tables and I could look up all of my properties. So we'll go to the steam tables and we'll look up, I'll record S1 and H1. And then in terms of my exit stream, I know that S2 is going to be equal to, where I write down, negative S1. So once I know S1, I know S2. So then I know S2 and P2. I could use that to go to my steam tables and read off everything else. Read off, say, enthalpy and whatever else it may be that I want. Okay, so let's get all of our properties, and then once we have that, we'll know the temperature by finding our place in the steam tables, and then we'll be able to calculate the work. All right, so let's do it. So I'm just going to make a little table here. So T1 is 450 degrees C. Okay, and P1 is 30 bar. Okay, I don't know T2, but I know that P2 is equal to 8 bar. Okay, so let's do it. So I'm going to go to my steam tables, which I think are hidden behind one of these. Here we go. Okay, so I'm going to go to my steam tables, and my initial state I'm going to assume superheated. Okay, so I'm going to go to my superheated steam tables, and we'll find out. Okay, so I'm going to go down to 30 bar. At 30 bar, my saturation temperature is 233.86. So since my temperature is greater than Tsat at that pressure, I must have a superheated vapor. Okay, so that's great. Let me come over here and we'll note we have a superheated vapor. Okay, so then I'm going to find my column of 450 degrees, and I'm going to read off H1 and S1. Okay, so 30 bar, 450 degrees C. Here's H1, 3344.7, so 3344.7. 3344.7, and then S1 at 450 degrees is equal to 7.0853. Okay, this is kilojoules per kilogram, and this is equal to kilojoules per kilogram Kelvin. All right. And before I even look up say 2, I already realize I'm foolish, right? So S2 minus S1 is equal to 0. So it's not S2 is negative S1. S2 is equal to S1, right? They're the same. It's isentropic. So my apologies. Just had a mental moment there. Okay, so now that I have S1, I know S2 is equal to S1, and that's going to be equal to the 7.0853 kilojoules per kilogram Kelvin. All right, so now what I'm going to do is I'm going to go to my steam tables. I'm going to stay in the superheated steam tables, and I'm going to find a pressure of 8 bars. Bam. Okay. Now what I'm looking for is an entropy of 7.0853. So it looks like I'm pretty close to 250 degrees. That's 7.04. But it looks like I'll be between 250 and 300 degrees C. Okay. So I'm going to need to interpolate. Okay. So I'll need to interpolate. But let me make a table here. And we will interpolate everything else. Okay. Okay, so I'm going to create a top column with my temperature in degrees C. Okay, then I know my entropy, so we'll call it S2, or just call it S. And then I'm also going to want to pull H1. All right. So we are at 8 bar. Okay, I've got 8 bar and 7.08. Okay, so 7.08 is between these two. Okay, so I know I'm between 250 and 300. So I'm going to be between 250 degrees C. Okay, I don't need to write that. And 300. The entropy of my system is 7.0853. Okay, so I'm going to look up the entropy and enthalpy at 250 and 300 degrees C. Then I'll use my known value of S to interpolate to find T and H. Okay. Okay, so at 250 degrees here, okay, S is, oh, I'm at 8 bars, is 7.0403. 7.0403. All right, so I expect I'm really close to 250. And H is 2950.5. Okay, now let's look at our properties at 300. 300 entropies 7.2345. And H is 3056.9. Okay, so I need to interpolate to find my temperature and enthalpy. Okay, so let me try and get MATLAB on top here. And so let me create interpolating. So I'll call it T2 and H2. Okay. And yeah, so let me call this, create a vector of my temperatures. Okay, so I have 250 and 300. And let me create a vector of my entropies. So I want the first and final. So 7.0403, 7.2345. And I need a vector of my enthalpies, 2950.5 and 3056.9. Okay, got them. So let me interpolate to find T2. So it'll be interp. Oh, and so let me write, I got to record S2 because that's going to be our animal that we're using to interpolate. So 7.0853. Okay, so I'm going to use MATLAB's built-in linear interpolation function. So I'm going to interpolate. So my independent variable, right? My x variable is s. Okay, my dependent variable, if I want to get t first, would be tk, and I want to estimate the value of tk for this known value of s2. And then if I want to get h2, okay, it's going to be exactly the same, only tk I replace with h. Okay, so let me call this chapter 6.4. Okay, and we'll get the value of T2. We said it should be close to 250, so yeah, we get 261.586. Okay, so we estimate 261.586. And then let me delete the K here, just because these are temperatures in C. I don't want to confuse myself. Okay, those are really temperatures in degree C. So my temperature is 261.586, and H, so this is 1,000, 2,975.2. So 2975.2. All right, so this is, our state 2. Okay, so I have H1 and S1. Okay, now I have T2 and H2 as well. Cool. Okay, so first part of the question, determine the exit temperature. Okay, if operation is reversible, well, we have the T2 is equal to 261.586 degrees C. So we have temperature. Now it wants to know the work. So I have the exit temperature. Okay, the question's now determine the amount of work. So work and exit temperature. So let's get the work now. And now that we have our inlet and exit are fully specified, hopefully it should be straightforward. So to get my work, okay, I'm going to write down my first law of balance for my open system. And so that's going to take the form of du total dt plus delta. Okay, I'm going to change in kinetic energy plus potential energy plus enthalpy. Okay, again, enthalpy, not internal energy, because I need to account for the work of that fluid element displacing the fluid element in front of it. If I look at H, all right, if I take that to be my specific enthalpy, I multiply by my mass flow rate. So if this is, energy per mass, this is mass per second. H times m dot gives me the correct units of energy per time. Okay, and that's going to be equal to Q plus W. All right, so now we simplify. Okay, so simplification 1 is I'm going to assume that we're operating at steady state. And what that's going to do for us is that'll mean that du total dt is equal to 0. That also will tell me that my mass flow rate, right, is constant. So, m2 is equal to m1 is just equal to, m. Okay, so we'll assume steady state. Okay, next assumption is I'm going to assume that my change in kinetic and potential energy is negligible. So I'm going to assume my change in kinetic energy and potential energy is negligible. Okay, and third, okay, we're told that our system's insulated. So just as we've already assumed, right, we're going to take that to be that Q dot is equal to 0, right? That my system's adiabatic. All right, so in doing all of that, okay, my first law reduces to, so delta H is H2 minus H1 times m dot is equal to W dot. Okay, now remember W dot, this is just energy per time. So you can think of it as my extensive work per unit time. M's mass per unit time. So if I divide through by m dot, right, W dot over m dot is just equal to W, right, energy per mass. So my first law of balance, right, if I'm trying to solve for W, reduces to H2 minus H1 is equal to W. Okay, so we have H2 and H1. I just need to enter H1 on the sheet. Okay, so let me get that. So H1 was equal to 3344.7. And I'll get S1 on there just because if I need entropy generation or that for the irreversible case, let me just get it up there just in case I need it. All right. So to calculate W, okay, W is just H2 minus H1. Okay, and we're just using values of enthalpy from the steam tables. So W will have units of kilojoules per kilogram. Okay, so W is negative 369.545. So W is negative 569 point negative 369 545. And that's going to be kilojoules per kilogram. Okay, it's negative. That's good because we know that our system's doing work. All right, so our system's doing work, our turbine's generating work, so our work is negative, so that's good, right? We're producing work. All right, so we've got the exit temperature and the amount of work for a reversible operation, so that's good. Now B says repeat the calculation assuming an efficiency of 80%. So repeat the calculation assuming an efficiency of 80%. Okay, and then how much is the lost work due to the reduced efficiency? All right, we've got this. Okay, so in B, we're told that the efficiency of our turbine is 80% or 0.8. Okay, so what our efficiency is going to be equal to? Okay, our efficiency is going to be equal to the actual work divided by the work that we would get from reversible operation, which is what we just calculated up here. Right, so let me just put a superscript rev up there to make it clear. Okay. So therefore, the actual work is 0.8, my efficiency, times my reversible work. Okay. So let's start by computing W. Okay. So back here, I'm going to update that to call it W rev. Okay. I'm going to create my efficiency. Okay, so my efficiency is 0.8. And so my actual work is my efficiency times my reversible work. Okay, so my actual work that this will produce is negative 295.6360. So this is going to be negative 295. So negative 295.6360. That's kilojoules per kilogram. All right. Now what they want us to get up to is, so I've got the actual work, but then they want to know how much is the lost work due to the reduced efficiency. So I want to calculate W lost, right? And I know that W lost is equal to T naught times, so T naught should be our bath temperature times S gen. Sorry, I've got to think here for this one. All right, so what we want to figure out is what part of that work is due to my entropy generation. So since we know W, okay, based on the efficiency, let's see if we can't work backwards. Okay. All right. So let's just work backwards and let's characterize our system based on this work and see what we can unravel. Okay. All right. So now that I know the work, right, what I can do is I can go back, and we showed right in the last problem that my first law balance for my open system reduces to H2 minus H1 is equal to W. All right, so I have the H2 minus H1 is equal to W. Now in A, when we analyze this, right, we assume that we had reversible operation, and we use that to solve for T2, which we use to characterize our system. So here, though, we don't know T2, right? So T2 for the reversible case is 261.586 degrees C. So what is T2 for the reversible case? Well, I know P2. Okay, what I can do here is I can solve for H2, a second intensive property, to pin down the state of my system. All right, so I know H2 is going to be equal to H1 plus W. Okay, so let's do this. Okay, so let me actually save a copy of this just so I don't confuse all of these twos and such. Or how do I want to do this? Just trying to think out loud because H2 is going to be different now. So let's think of this non-reversible. Okay. So let me just clear H, S2, T2, and H2. Yeah. Okay. So I'm going to clear S2, H2, T2, and I'll clear S and H. Okay. All right. So now what I'm going to find, okay, is I'm going to calculate H2, and H2 is going to be equal to H1 plus W. Okay, so I get H2 now is this, 3049.1. Okay, so now I have that H2 is equal to 3049.1. That's going to be kilojoules per kilogram. And the other piece of information I know about my exit stream is P2 is 8 bars. Okay, so the conditions of my exiting stream are fully specified. All right, so what I'm trying to think through here still, the process is adiabatic, right? We're told that we can assume that this is insulated. All right, so it's still going to be, when I go to my entropy generation term, okay, that the delta S of my bath is going to be 0, right? Because it's adiabatic. There's no heat exchange between my system and surroundings. So I know that term's 0, okay? But now what I'm going to get is, since Sgen is not going to be equal to 0 for the irreversible case, I know that delta S of my system is not going to be equal to 0. So I know now in this case, my process is not going to be isentropic, right? S2 is not going to be equal to S1. Okay, so I want to get characterize my system here. Let's see if I can get my new T2 and then S2, just like we did for the reversible case. And then we can use that to get delta S of our system, which will be equal to Sgen. So then we'll get our entropy generation. And then let's get that, and let's think through it a little more, right? So take this one step at a time, okay? All right. So my apologies. I'm just trying to make sure I'm keeping track of everything as I work through this. These can get a little long. All right. So I'm going to go to my steam tables again, which are now hidden. Okay. So now at 8 bar, okay, I'm reading across enthalpy for 3049.1. Okay, and I see that I'm going to be between 250 and 300 degrees again. Okay, hey, that's right where I was last time, right? I was right between 250 and 300 last time as well. Okay, so let me go over to my script then, because I actually have everything tabulated already. Okay, because since I'm between 250 and 300, all right, what I'm going to have is I'm going to have the same table. So I guess let me just go ahead and write it down because now we're going to be interpolating with T2. Okay, so let me just collect everything, just again, just for completeness. So I'm going to be between 250 and 300 degrees. Okay, I can keep entropy as my middle column, that's fine. But now I know the enthalpy of my state of interest, which is 3049.1. Okay, so let's go look up or get our properties at 250 again. So S was 7.0403. Okay, H was 2950.5. Okay, 300. S was 7.2345. And H is 3056.9. All right. So let's pop up MATLAB. It's hiding back here. Okay, so actually, I'm gonna undelete T, S, and H. Right? Why? Because that's the same exact data I just tabulated since we're between 250 and 300 degrees C. Okay. Okay, and so what I'm actually going to do is I'm going to copy this line here. Okay. So my new T2 is I'm going to interpolate not with independent variable S, but H in TC. So I want the value of TC, my temperature, for that known value of H. And then to get the entropy, okay, I'm going to interpolate. My independent variable again will be H, right? Because I know the value of H in my final state. And instead of temperature now, I'll have our entropy data. So interpolating, now I get T2. Okay, so now we're temperature is 296.3177. Okay, and my entropy is 7.2202. Okay, and so this corresponds to our new state 2. All right, so let's calculate our entropy generation. Okay, so again, thinking back to chapter 4, Sgen is going to be delta S of my system plus delta S of my surroundings. Okay, or if I take my surroundings to be a bath, this is delta S of my system plus delta S of my bath, where delta S of my bath is equal to Q bath over T bath, which would be negative Q over T bath. And since our system's insulated so that this process is happening adiabatically, Q is equal to 0. Okay, so what I'm left with then is Sgen is equal to delta S of my system, and that's going to be equal to S2 minus S1. All right, so I know S2, so Sgen then is going to be equal to S2 minus S1. So my entropy generation is positive, good, just like it should be, of 0.1349. So Sgen is going to be equal to 0.1349. That'll be kilojoules per kilogram Kelvin. All right, so what do we have? So from our efficiency equation, we calculated our actual work. And with our actual work then, we're able to solve for H2 from our energy balance. And then once we had H2 and our pressure is 8 bar, we're able to go and find the corresponding temperature and entropy. And once we had the temperature and entropy, we were able to calculate delta S of our system, which is equal to Sgen, which is going to be equal to 0.1349. All right, so now we have the entropy generation. And so now you want to look at the lost work. Okay, so what am I doing here? So we just went and we calculated Sgen because we could. Bear with me for 1 second. I'm just trying to think through this for a second. Yeah, so we have Sgen I'm having a mental moment. So we could calculate the difference in work output for the reversible process relative to the actual process. And I mean, that's just going to be equal to 0.2 times the reversible work. And interestingly, from that, we're able to fully characterize our system. Yeah, we were able to fully characterize our system and even went so far as to calculate the entropy generation. So I think that that's all we could do. Yeah, so the lost work, right, should be just the difference in our reversible work and the actual work that we achieved, right? And so the lost work due to the efficiency should just be equal to 0.2 times my reversible work, right? Which should be this negative 73.90. Okay, so the lost work, W lost, should be equal to this negative 73.909. Okay, kilojoules per kilogram. Okay, and that's just the difference in the actual work output and the work that would be achieved via reversible operation. So, all right. So I hope that helps. I think we fully characterized the system. Hopefully it helps. If you have any questions, by all means, just let me know, okay? We'll see you in the next example. All right, this is just a follow-up on problem 4. I had a moment at the end in terms of part B, trying to figure out the wording here. How much is the lost work due to the reduced efficiency? All right, and so in part B, we worked backwards. So based on the efficiency and the reversible work from part A, calculate the actual work. And so I just said, oh, the lost work would be the difference between the reversible work and the work that's actually produced, right? And that's fine, right? And that difference has to be due to the inefficiencies of the process. But anyways, once I had work, right, we had worked backwards, so we were able to write our first law of balance, calculate H2, use that to characterize our system, and get our entropy generation. Where I was, a little thrown back is in the text, right? They define the lost work as being T naught times S gen, right? Where T naught would be the temperature of your bath. And the general idea of where this comes from is, if I think of the first law of balance for this process, where if I write it out in general, I'm not going to kill. So I'm going to where I worked out our first law of balance. Here, right, we're going to do everything except C, in which we assume Q is equal to 0. Right? And so if you write down our first law of balance, except for assuming Q is equal to 0, we get H2 minus H1 is equal to Q plus W. Okay. Now from our entropy balance, right, we get S gen is equal to delta S of my system, which I'll take to be, or just write as S2 minus S1, plus delta S of my bath, or my surroundings, which would be negative Q of my system over T bath, which they write as T naught. So the idea is if I take this expression, okay, and I solve for Q, I get that Q is equal to T naught times S gen. Hold on, I've got to get my order right. No, it's T naught times S2 minus S1 minus S gen. So then if I plug this in to my first law of balance, what I end up getting is H2 minus H1 is equal to T naught times S2 minus S1 minus, okay, this is T naught times S gen, right? T naught times S gen. So T naught S2 minus S1 minus T naught S gen plus W. Okay, so solving for W, I get W is equal to H2 minus H1 minus T naught S2 minus S1 plus T naught S gen. So the idea is for a reversible process, okay, for the reversible process, S gen would be equal to 0. Okay, so for the reversible process, my entropy generation would be 0, all right, and I would be left with my work is equal to this. Okay, so with a, attribute this then it to would be the reversible work. Now this is the reversible work given those inlet and outlet conditions. All right, this is the reversible work given those inlet conditions. Okay, and so then they take this part, right, which is due to my entropy generation, and they chalk that up to being my lost work. All right, so they take W lost to be equal to T naught times S gen. Okay. Where this is a little, where I was having my moment in my head is thinking about this equation, right? The challenge though is our system's adiabatic, so there's no heat exchange with my bath, and we're not even suggested what the temperature of our bath might be, and so that's where I had my moment, right? But I think the key is given that we have the conditions of our inlet and exit pinned down, okay, this would be the reversible work, okay, and so then this they're going to attribute to the lost work, okay. Where it just becomes a little odd is there's no, we're not thinking in terms of a T naught. Okay, and so in the example problems, they typically just assume a bath temperature of 25 degrees C. All right, so they would just take T naught to be equal to 25 degrees C, which would be 298.15 Kelvin. Okay, and so with that T naught and our calculated value of S gen, all right, they could estimate a W lost. So you'd end up getting a W lost of, so I still have this open. So I'll call this T loss 1, what I called it. But W lost, all right, so I need a T naught of 298.15. So they would define W lost as being equal to T naught times S gen. And so with that formula, the work lost is positive, and it's 40.2198. Okay, so the work lost is 40.2198. And that's kilojoules per kilogram. All right, so looking now where mine was negative, it's because I had it as 0.2, but it should actually be what? My actual work minus my reversible work, which should be positive, right? So, okay, let me have my mental moment. So we should get the same value, just the sign would be different. Okay, so the lost work is actual minus reversible, which is equal to eta times the reversible work minus my reversible work. So that's my reversible work times eta minus 1. Okay. So W lost then would be a negative 0.2, right? So it's the value I had before was correct. It's just the sign needed to change. Okay, so when I computed the difference, I just needed to change the sign to get that right. All right, so I had 73.909. Okay. My value is higher, right? At the same time, one potential issue is when I look at my turbine, right, I have an inlet of 450 degrees C, and my exit's, 261 degrees C. Okay, that's much greater than this T naught, which would assume a bath of 25 degrees C. Right, so we're assuming that our bath is 200 degrees cooler, right, which would definitely affect this, right, since this is a multiplicative term. Okay, so there it is, right? So there's W lost, the equation to give in the book. That's where it comes from. My mental block was we're not thinking in terms of a bath. It's adiabatic, but that's what the definition of lost work is. My apologies. Hopefully that helps.